In this lesson, we will discuss the solutions to linear congruences. So a linear congruence is a congruence that's equivalent to one of the form ax is congruent to some integer c mod m. So this is an example of a linear congruence. The question we're interested in is for integers a, c, and m, can we find a solution find an integer x such that ax is congruent to c mod m. Okay, so we'll answer this question explicitly. We'll know when we can find a solution to this linear congruence. Well, if there is a solution to this congruence, then m must divide ax minus c. Okay, so if a solution exists, then m divides ax minus c. So ax minus c is an integer times m, and we want to write this as m times the integer negative y for some integer y. Okay. The reason why I'm writing it that way is so that when I rearrange this and solve for c, we have the linear Diophantine equation ax plus my equals c. And we showed that this linear Diophantine equation is solvable exactly when the greatest common divisor of a and m divides c. So in this linear Diophantine equation, is solvable exactly when, so if and only if, the greatest common divisor of a and m divides c. So we see that if the greatest common divisor in a and m does not divide c, then this linear congruence has no solution. So if the GCD of a and m does not divide c, then the congruence ax congruent to c mod m has no solution. So now let's consider the case when the greatest common divisor divides c. Okay, so suppose the greatest common divisor, I'm going to call that d. So d is the greatest common divisor of a and m. So suppose this divides c. Okay. Then we showed that there's a general solution to the Diophantine equation ax plus my equals c. Okay. And then each solution of ax plus my equals C has the form x is going to equal some particular x solution plus m over d times t, and y equals some particular y coordinate of a solution minus a over d times t, okay, where x0 and y0 make up one particular solution, and t is some integer. So this is the general solution to ax plus my equals c. So these x coordinates, these x's given by this expression right here, all satisfy, for any value of t, these x's will satisfy the congruence ax is congruent to c mod m. So the values of x, which is some particular solution x0 plus m over d times an integer t for an integer t, these values of x are solutions to the congruence ax congruent to c mod m. So therefore there are infinitely many solutions to this congruence. For any value of t, any integer value of t, we can produce another solution to this congruence. So there's infinitely many solutions to this congruence when d divides c. Thus there are infinitely many solutions to this congruence when d divides c. So when the greatest common divisor of a and m divides c, there's actually an infinite number of solutions. But next we want to discuss how many incongruent solutions are there. So we know there's an infinite number of them, but are they all congruent to each other, mod m? Okay, so this is the next question we're going to address. How many mutually incongruent solutions are there to this congruence? How many mutually incongruent solutions of ax congruent to c mod m are there? Okay. Well, so we know there's an infinite number of them. We're assuming, that, again, that d divides c. So there's an infinite number of them. Let's suppose that two solutions are congruent. So suppose two solutions are congruent. Mod m. Then remember, these solutions look like x0 plus m over d, I'm going to say times t1. That's one solution. Suppose that's congruent to x0 plus m over d times t2 mod m. Then we can subtract x0 from both sides to obtain m over d times t1 is congruent to m over d times t2 mod m. So now I'd like to cancel or divide both sides of this congruence by m over d. But I've got to worry about changing the modulus m. Well, let's look at the greatest common divisor of m and m over d. Well, since the greatest common divisor of m and m over d would have to equal m over d, okay, because m over d is a factor of m, then when I divide both sides of this last congruence by m over d, I've got to divide the modulus by m over d as well. Okay, so we can divide by m over d and replace the modulus by, well, if I take m, I'm going to have to divide it by m over d, and that reduces to d. So when I divide both sides of this congruence by m over d, I have to divide the modulus by m over d, and so the result is that t1 is congruent to t2 mod d. So if two solutions of this congruence are congruent mod m, then we've just shown that the integers t1 and t2 must be congruent mod d. Okay, so how many different ways could I have integers mod d? How many residues are there mod d? Well, there's d residues mod d, and so we see that there's d different possibilities for integers t, for residues of integers t. So there are d residues mod d, and therefore by letting t be one of these d residues, okay, so by letting t be an element of the integers mod d, we get that there must be d mutually incongruent solutions to this congruence, to the original congruence, to ax congruent to c mod m. So we can actually write out a representative of these d mutually incongruent solutions. x0 plus m over d, x0 plus 2m over d, x0 plus 3m over d. Okay, so I'm letting the integer t be 0, 1, 2, 3, and so on up to d minus 1. So x0 plus d minus 1 times m over d. So these are all mutually incongruent solutions to the original congruence. So we have completely determined the solutions to any linear congruence. Let's summarize our knowledge of these solutions as a theorem. So if D is the greatest common divisor of A and M, then the congruence AX congruent to C mod M 1 has no solution if D does not divide C, and 2, this congruence has D mutually incongruent solutions mod M if D divides C. So in fact, we already demonstrated that if we have a particular solution x0 to this congruence, then x0 plus m over d, x0 plus 2m over d, and so on up to x0 plus d minus 1 over d times m. These form a complete set of mutually incongruent solutions. So let's solve a linear congruence. In this example, we want to see if it's possible. We want to find a complete set of mutually incongruent solutions of the congruence. Okay, so first let's look at the congruence 27x. It's congruent to 10 mod 51. Let's look at the greatest common divisor of 27 and 51. Well, we see that the greatest common divisor of these two integers is 3. And since 3 does not divide 10, this congruence has no solutions. Here's another example. Now the congruence I'm going to start with is 9x is congruent to 15 mod 24. Well, the GCD of 9 and 24 is 3. And we know that 3 divides 15. So there are solutions. In fact, the greatest common divisor tells us how many mutually incongruent solutions there are. So in fact, there are 3 mutually incongruent solutions. So we know there's 3 mutually incongruent solutions. Let's solve this congruence. Well, 9 and 15 are divisible by 3. So when I divide by 3, I've also got to divide the modulus by 3. It's not relatively prime to 24. So that we get 3x is congruent to 5 mod 8. Well, if I can add 8 to 5 to get 3x is congruent to 13 mod 8. I'm looking for a multiple of 3 here. So I'm going to add 8 one more time. So 3x is congruent to 21 mod 8. And since 3x is congruent to 21 mod 8, I can divide by 3. And 3 is relatively prime to 8. So x is congruent to 7 mod 8. But I wanted a solution to a congruence mod 24. Well, if x is 7 mod 8 and 24 is a multiple of 8, then x will also be congruent to 7 mod 24. So since x is congruent to 7 mod 8, x will also be congruent to 7 mod 24. So this is one of our solutions, and so we're going to add multiples of m over d, the modulus divided by the greatest common divisor. Okay, so note m over d for this example is 24 divided by 3, which is 8. So I'm going to add multiples of 8 to our first solution. So we see that if x is congruent to 7 mod 28, then x congruent to 7 plus 8, or 15 mod 24, is also a solution. And if I add 8 again, 15 plus 8 is congruent to 23 mod 24. So these are the other incongruent solutions. So the complete set of mutually incongruent solutions are x is congruent to 7, 15, or 23 mod 24. And so you can verify that we have solutions to a congruence just like we can verify a solution to an equation. You could plug 7, 15, and 23 back into the original congruence and see that we do get a solution to the congruence. So we've established that if the greatest common divisor of A and M divides C, then there's D mutually incongruent solutions. Well, what if A and M are relatively prime? Then the greatest common divisor would be 1, and so there must be a single unique solution mod M to that particular congruence. So as a corollary, we see that if the greatest common divisor of A and M is 1, then there is a unique solution mod M to the congruence AX is congruent to 1 mod M. So if we look at this congruence, we have an integer a, and I multiply it by x, and that is congruent to 1 mod m. So it looks like when I multiply these two integers, a and x, I get the identity 1. So this leads to the definition of a multiplicative inverse mod m. So let's define multiplicative inverses. So for relatively prime integers a and m, the multiplicative inverse of a, denoted by a with a exponent of -1. Okay, so the multiplicative inverse of a is the unique solution mod m to the congruence ax is congruent to 1 mod m. So we see that a times its inverse will be congruent to 1 mod m. So let's look at some examples. So notice that when working mod 11, 5 times 9 is 1 more than a multiple 11. 5 times 9 is 45, and that is congruent to 1 mod 11. So we say that 9 is equal to the inverse, multiplicative inverse of 5 mod 11. So suppose we had a congruence like 5x is congruent to 7 mod 11, and I know that 9 is the inverse of 5 mod 11, so I'm going to multiply both sides of this expression by 9. So I see that 45x is congruent to 63 mod 11, but 45 is 1 mod 11, so I just get x on the left hand side, and 63 is 8 more than a multiple of 11, so x is congruent to 8 mod 11. So let's look for all of the inverses of integers mod 11. So an integer will have an inverse if it's relatively prime to 11. Well, let's look at all the relatively prime residues. So we know there's 10 relatively prime residues mod 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let's look at their inverse mod 11. Well, 1 is going to be its own inverse mod 11, because 1 times 1 is 1 mod 11. Think about the number 2. 2 times 6 is 12, which is congruent to 1 mod 11. So 6 is the inverse of 2, and therefore 2 would be the inverse of 6 mod 11. We've already established that 9 is 5's multiplicative inverse, and therefore 5 is the multiplicative inverse of 9. 3 times 4 is 12, so 3 times 4 would be congruent to 1 mod 11, and therefore 4 times 3 is congruent to 1 mod 11. 7 times 8 is 56, which is 1 more than a multiple 11, and 8 times 7 is also 56. And 10, we see, is actually its own inverse mod 11, because 10 times 10 is 100, which is 1 more than 99, a multiple of 11. So here's the list of all inverses of residues mod 11. So in general, if the greatest common divisor of A and M is 1, then A has a multiplicative inverse mod M, and the congruence AX is congruent to C mod M is solvable. We can multiply both sides of this congruence by A inverse, and we see that X will therefore be congruent to A inverse times C mod M. And this must be the unique solution mod M, because the GCD of A and M is 1.